everything?
So for Suzuki coupling, the heck coupling is a little bit much more specific in terms of so just the heck coupling is when we take the benzene ring with our bromine, but really the only molecule we can add in the heck coupling is just the double bond. But Suzuki is a little bit more generic and a little bit more broad, because all I have to do is basically take my borate ester and add to it whatever R group I want, and then I'm going to couple and then using the palladium usually on carbon, and I'm just going to use the K2, the potassium carbonate and water. You're going to couple the benzene ring to whatever R group was on the boron. So the question is, how do you make this? How do you add the R group to the boron? And there's two different methods to do that. If you start with a double bond, so let's say we just start, is this a generic double bond? And we add to it our borate ester. This is going to add exactly like BH3 did. So just kind of as a quick review, when we had our double bond and we were adding to it BH3 and H2O2, the first step in that process was that we added the boron and the hydrogen. So if I treat this like an H with a BH2, I added the hydrogen and the boron 100% cis. And the boron had to go on the least hindered carbon. So in this particular case, if I added it to this double bond, what would happen is the hydrogen would go on the tertiary carbon and the BH2 would have gone on the least sterically hindered carbon. So then what happened was, because remember it's BH3H2O2, when I added the hydrogen peroxide, the BH2 just got replaced with an OH group in exactly that same position. So the BH2 basically would then have been replaced by the hydroxide. So that's how we know that this one was anti-Markovnikov 100% cis. So this reagent, this hydrogen with the BOR groups, is going to do exactly the same thing. We're going to add the H and the boron to any double bond 100% cis, with the boron group going on the least hindered carbon. So if I use this as my model, I would end up adding the hydrogen here and then the BOR2 group on the other carbon. And since this isn't cyclic, then I can put bold wedges in here, but they're kind of irrelevant because there's no chiral centers in this molecule. And now once I have that boron, so what I have to do is I have to choose a double bond that gives me the R group over here, that gives me the right R group that I want, to then be able to add to the benzene ring depending upon the group that I want to add on the ring. So in this case, I would be adding that entire group, which would be, and you have to make sure you put this bond in, and sometimes it's better if we just wrote the groups out. So we've got a CH2, and then we've got the two CH3s. So this would be with the palladium, carbon, K2CO3. When I couple those two together, so if this is the group I want to add, I've got to get that group by adding the borate ester to the proper double bond. That's kind of the long answer of the first way to do that. Most likely what I'm going to ask you to do is to write the product of the reaction. But if you do synthesis problems, which are going to be for today's video, then you just have to think backwards. Okay, how am I going to get this this group? And then you'd say, okay, I need a double bond. This is my connection point. So that's where the boron needs to go. Does that make sense?
Working on it. So this is random. Maybe I just lost you. Where did that HB or HBH3 come from?
So what I'm doing here is, I'm relating this back to last semester. So down here, last semester, when we dealt with boron, it was with the alkene plus BH3 H2O2. So this was last semester's alkene reactions. Now, it's possible you could have used B2H6 instead of BH3. But basically we're reacting with BH3. So the idea is that overall, I always ask people just to go from here all the way over to the final alcohol. But the first thing we did was the way that we got to that alcohol was by adding the H in the boron 100% cis, with the boron going to the least sterically hindered carbon. And then in the second step, the hydrogen peroxide was the one that came in. The hydrogen peroxide came in and replaced the boron in exactly the same position with the OH. So this reaction was 100% cis, anti-Markovnikov. But what I'm now saying is, this was our first step. Add this BH3 now as an H, BH2. Add the H, the BH2, 100% cis, boron on the least sterically hindered carbon. What I'm doing when I come up here is I'm saying this is exactly the same reaction with an H with a BOR2 group instead of a BH two group. So I'm adding the H and the boron, anti-Markovnikov 100% cis, but now that group that I just added the boron to is what I'm going to couple to the ring to form the final alkyl benzene. So this is just the analogy of what we did last semester to what we're doing now. It's very much the same thing in that first step.
Okay, and it has to add, so that like CH2 will always add because it came from, like, it is what was attached to the boron. Just like for direction's sake, like that's the one that'll always add. It won't add from the opposite side.
Which one?
So I wish I could point. So like right where your mouse is, like that, whatever group is attached to the BOR is what's gonna attach to the ring.
Yes. So let me save this and let me pull up a new one. So when I have that molecule where here's my BOR groups. So this group right here in red is what's going to add to the benzene ring. So the boron is the boron and the bromide and the Br are going to go. So when I do my coupling, so when I couple that, I'm going to couple the benzene ring, then replacing the bromine is going to be the red group. So it'll be, and I'm going to put a, because you always have to have the bond, then the red group. So then the red group would look like this. So what I'm doing is I'm coupling, and maybe what I should do is this, maybe. So the blue bond is the one that's being formed. So what I'm doing is I'm coupling the benzene ring with the alkyl group. So wherever the boron was and wherever the bromine is, I'm going to couple those two groups together.
Can we do an example of a phenol reaction with the William ether synthesis?
Did everybody see, well, I sent an email out last night that what I did yesterday was I put online some list of aromatic reactions, which will be helpful for today's video. So I listed all the different transformations that you can do. And so one of the transformations that we have to be able to do is to add an OR group to the benzene ring. So the way that we're going to do that is we're going to take, and first of all, we need to get the OH group on the ring, and then we can go from there with the Williamson ether synthesis. So you see, somebody asked for this on Piazza. I thought it was worthwhile, although when I give an exam and you have access to all the notes, then I guess it's going to be relatively easy to use those. Okay, so what we do is, if we're going to add an OR group to the benzene ring, I need to put the OH group on there first. Then I'm going to deprotonate that alcohol. Okay, it's called a phenol, but it's really just an alcohol. So we talked about before taking an alcohol and deprotonating it and making the alkoxide. Now for an alcohol, I think we said you could use a C-, you could use an H-, and you could use NH2-. So once you make the alkoxide, then you can add to it any primary or secondary halide, because I'm basically going to do an SN2 mechanism. So the O- is going to come in, kick the chlorine off, and I'm going to end up then adding that group and forming the ether. So this was a Williamson ether synthesis. So all I'm doing up here is I'm doing the same thing. I want to turn instead of the alcohol becoming the alkoxide, I want to turn the phenol into what's called a phenoxide. So same reagents, a C minus, maybe I could use an H minus, maybe I could use an NH2 minus, but phenols are more acidic than alcohols, so I can also just use hydroxide. So any of those bases will deprotonate the phenol to make the phenoxide. And once I have the phenoxide, I have the same set of rules that I have for the alcohol or the alkoxide. So in other words, I can react that with either a primary or a secondary halide, and it's still going to do an SN2 reaction. So the O minus is going to come in, add to the carbon, kick off the chlorine, SN2, so that I'm going to be able to add my same alkyl group. Well, I forgot the oxygen there. So I'm going to be able to make the ether. It's just in this case, on one side of the ether is the phenyl group, as opposed to another alkyl group. So that's the same thing. That's Williamson.
Thank you.
Does that help, Isabella?
Yeah, that helps a lot. Thank you.
And then the only thing I suppose I should add is, why does it have to be primary and secondary? Because if you tried to take the phenoxide, if I have that deprotonated phenol and I tried to add to it like a tertiary alkyl halide, it won't undergo SN2, it'll undergo E2. Just like the Williamson ether synthesis did before. So in that case, I would end up with the phenol and I would end up with the alkene. So that's the only restriction on why it has to be primary and secondary.
So what would a secondary one look like?
Like a secondary reaction.
Yeah, would it just pick one of the carbons?
So,
Or the most
well,
substituted one?
basically, a secondary would look like this. If I put two R groups on here, then that's a secondary alkyl halide. So there would be two R groups over here.
Can we do an example with the lithium cuprates?
Sure. Any specific example or just anyone?
I don't know. There was just ones in the video yesterday when I watched it. I was just like confused with them.
Okay. So all of these, okay. All right, let me take it from the beginning and say, if you had we know that we could take the alkyl halide and react it with magnesium, and we could make we could make the anion. Basically, we can make the Grignard reagent. And that Grignard reagent is both a strong base, it's also a strong nucleophile. So one of the things that you might think about, because all the carbon-carbon bond forming reactions that we did, including Grignards and Diels-Alders, those are like of the highest importance in organic, is to be able to form a carbon-carbon bond. So at some point somebody said, well, if this is a strong nucleophile, why can't I react it with a halide and do like an SN2 reaction on it? And they tried, and the problem is it doesn't work. So it's a good idea to say that you can have a C, that if you made the Grignard with the C minus, that it would do an SN2 reaction, but the problem is you don't get that reaction. So then they tried it, instead of with magnesium, they tried it with lithium. The difference between magnesium and lithium is just simply that you end up with an anion with only the lithium as the counter ion, because lithium is only +1 and magnesium's +2. And they tried that reaction with just the lithium, and basically that didn't work, so there was no reaction there as well. So somewhere along the line, somebody decided to throw in copper into this. So what they found, and it was Gilman who found, that if you took your anion with the lithium, if you took your organolithium compound and you mixed with it copper 1 chloride bromide iodide, what you end up doing is you end up forming this complex, which is going to have 2 -1 ions, a lithium plus, and a copper plus. So there's 2 pluses for basically 2 minuses. So this complex is what's called the lithium cuprate. Or it's also called the Gilman reagent. Okay, so far so good?
Yeah.
So this complex actually, because of the presence of the copper, would let me react. I'm going to need 2 because of the stoichiometry, but it will now basically do, and I'm going to put this in quotes, an SN2 reaction, where now I'm going to be able to couple my CH2 with my isopropyl group over here, so that now with the copper present, it actually does that coupling. So it's like Suzuki and Heck coupling. I'm taking this group and I'm going to couple it with this group to make that final product. But the presence of the copper is what lets me do this reaction, whereas up here it fails miserably. So in the benzene ring case, this is a way to add any group I want to the benzene ring. All I have to do is start out with a bromobenzene, react it with lithium, make my organolithium compound, react that with the copper, so now I'm going to end up with now I end up with this Gilman reagent. And so any group I want to add to the benzene ring, I now just have to say, okay, that group just needs to have a bromine attached to it. So if I wanted to add something like, well, let me start with something that might be the easiest one and just say, if I wanted to add a propyl group to the benzene ring, a straight chained propyl group, I could do that through this Gilman reaction so that I would end up with now adding the propyl group to the ring. Because remember, in order to add a straight chained alkyl group to the ring, we had to go through the acid chloride and then do a Wolff-Kishner or Clemenson reduction down. This is an alternative way to put a straight chained alkyl group on the benzene ring. But basically, any group over here that has a bromine on it, I can put now on the benzene ring. So I can make this group as complicated as I want.
So are there restrictions for what this can't do?
The restriction,
like a group we can't add?
Not for us. For us, if you want to be creative and make this group whatever you want, then it'll work. Now that might be a little bit of a problem if I would ask you how to synthesize this molecule, but we're not going to go there. So in real life, you'd actually have to be able to make whatever this molecule is. But there's no restrictions. The main restriction on this is that the Gilman reagent is still a carbanion, and so you have to avoid water, carbon dioxide, air, any acidic hydrogen like a carboxylic acid, an alcohol, an amine. You have to avoid the molecules that actually, that it would deprotonate because it is a really strong base. So, I mean, that's the limitation on it, because the Suzuki and Heck coupling use water as their solvent, and so they're much more environmentally friendly than any of these.
So I remember in the video that showed us how, I guess, long question short, could we add an OH to that?
No.
If we want, instead of doing all those other steps, should we have to do those?
No. The only way to make the OH is to go through. The only way to add the OH to the ring is to go through this series of sequences. Is to put a nitro. Let's see, where is that? Oh, it's up here. So if you want to put an OH group on the ring, you need to go through these series of steps. You need to, whoops, let me go back here. You need to go, oh, that's right, I don't have a spotlight in this mode. So you're going to add nitric acid to put the nitro group on. You reduce the nitro group to an NH2 group with iron or tin, HCl, and heat. You add the HCl and sodium nitrite to give the diazonium salt, and then you add H3O+. So this sequence of steps is the only steps we have to put an OH group on the ring.
Can we do a nucleophilic aromatic substitution problem?
Activated or deactivated?
Activated.
Activated. Okay. Okay, so what I'm going to do is I'm going to replace that chlorine. I have two sets of reagents I can use here. I can either use something like sodium hydroxide. I don't even know that I need a lot of heat for this, although I probably do, but we'll leave it out. So you can use sodium hydroxide, or you can use NH2 minus in liquid ammonia. So I can replace the Cl with an OH or an NH2 minus. Now the problem is that I'm doing nucleophilic aromatic substitution. So activating and deactivating mean exactly the opposite of what they did in electrophilic aromatic substitution. So in order to make this group activated, I need to put what we learned are deactivating groups on the ring. And I need to put them at the ortho position and at the para position. So this would be an activated ring because it has basically electron withdrawing groups, which is what I need. So there's two different mechanisms. There's one mechanism for the activated ring, and there's a mechanism for the unactivated ring or the deactivated ring. So in this case, what's going to happen is I'll do it with the NH2 minus. That's what quiz question was. I did in the video, I did an OH minus. But if you take the OH minus and erase it and put an NH2 minus, you would get the same mechanism. So the NH2 minus comes in and attacks the carbon that the chlorine is on. And then this double bond has to basically move to the carbon with the nitro group. So in the first step of the mechanism, I'm going to end up with a Cl and the NH2 with the negative charge on the carbon with the nitro group. So what I'm going to do is I'm going to write out the structure of the nitro group. So it's got an O minus and an N plus. So the reason that the nitro groups are going to stabilize that anion is because I can form 3 more resonance structures from this one. And the way I can do that is I gave myself enough space. So what I'm going to do is I'm going to take this pair of electrons. So one of the issues that we have in this problem is that we have to go back to kind of the beginnings of last semester when we talked about drawing resonance structures. So when you have a carbocation, you always move the pair of electrons towards the carbocation to make the resonance structure. When you have a carbanion with an extra pair of electrons, you always move that pair of electrons to form a multiple bond, but then you've got to break the other multiple bond and give it to the carbon next to it. So it's a different way of writing the mechanism than what we have been with carbocations. So in this case up here, well, first I should ask, does that kind of make sense?
Yeah.
So we have to move this pair of electrons to form a double bond with the carbon that the negative charge is with, but then we have to break the other bond and move it to the next atom in this case. So if I'm sitting here with my O minus, I could take this pair of electrons and I'm going to change the color on it, and I'm going to bring that O minus to form a double bond here. But then at the same time, I've got to take this pair of electrons and give it to the carbon that is attached to the other nitro group. So if I do that, I'm going to form, and I'm going to write it down here, a second resonance structure. So my Cl and my NH2 are going to be there, but now my negative charge is going to be next to the bottom nitro group. And my double bond will go there. So the reason that the nitro groups are necessary to make this activated is because the minus charge ends up next to both of the nitro groups. And since these are electron withdrawing groups, they can pull the electron density out and stabilize it. If these were electron donating groups, they'd be trying to push electron density into a carbon that already has a negative charge, and that would destabilize it. So these are two of the resonance structures that are possible. Okay, is everybody with me? Yes, no.
Yes.
This is the one thing we miss is, because if I have all these windows open and there's like 20 people, my internet decides to crash. So that's the only reason why I'm cutting down on the windows. Okay, so now if we come up to this molecule, we can write a second resonance structure. So what I'm going to do is I'm going to take this pair of electrons, and now I'm going to use it to form a CN double bond. I've got to move that pair of electrons from the NO double bond and give it to the oxygen to keep nitrogen from violating the octet rule. So the other resonance structure that you can draw is to have the double bond to the nitrogen, and now both of those are going to be single bonds with an O minus. The nitrogen still has a positive 1 charge. And I'm just going to write that as an NO2 group. So that's a second resonance structure off the top one. And then down here, I can do the same thing by taking this pair of electrons, moving it to form a CN bond, double bond, and then move the pair of electrons on the oxygen. So I can write a second resonance structure over here. So that now I have my double bonds. Now I'm going to have a double bond to the nitrogen with 2 O minuses. So those are our 4 resonance structures for this intermediate. And the ability to draw 4 resonance structures makes this intermediate, the intermediate here, the intermediate is going to be more stable because of all the different resonance structures. So that's what's going to make this an activated ring. Does that make sense?
Yes, thank you.
Okay, so then we need the final step. So in order to have to pull out a third color here, let me, and I'm saving all these screens, and actually I'm recording this, so I'm going to start putting it online. So if you missed any of this, you could go back. First of all these slides, I'll put these on right after class, because I'm getting caught up slowly but surely. By this weekend I will be, hopefully, but I'll put these on right afterwards. So if you miss something, you can go back and take a look at this, or you could, I don't know, print it out. So let me save this screen, let me clear it, and let me draw out that first resonance structure. And I'm just going to go ahead and put the NO2 groups in to save some time. So this was our first resonance structure with the minus charge next to the nitro group. So in order for the final step, I'm going to take this pair of electrons, I'm going to reform the double bond. I'm going to reform the carbon-carbon double bond and reform the aromatic ring. But if I do that, something's got to go, either the chloride or the NH2. So my question is, which one's going to go? And my choice is, which is a better leaving group, the Cl or the NH2? And remember that leaving group ability is based inversely on basicity. So chloride is a better leaving group because chloride is a weaker base than NH2 minus, so the chloride's got to go. And so I'm going to lose a Cl minus, and I'm going to reform my benzene ring. But now my NH2 has replaced the chloride. So that's why it's nucleophilic aromatic substitution, because I'm replacing the chloride with an NH2 minus. And if I used hydroxide at the beginning of this, then everywhere there's an NH2 minus, just replace it with an OH and you have the same mechanism. So that's the activated nucleophilic aromatic substitution.
So how would the deactivated go?
Okay, that was, I suspected that was going to be the next question. So now let me put a chlorine on here, but now let me put an activated group. So now this is non-activated or deactivated, because I'm missing the nitro groups to stabilize the negative charge. So if I was to react this with something like hydroxide, number one, it's going to take about 350 degrees of heat. So I'm going to really have to push this reaction because it's now not activated anymore. The mechanism has to change as well, simply because I don't have any groups in these positions that would stabilize the negative charge. So what happens is that this mechanism changes. So at 350 degrees, hydroxide can deprotonate things that it normally wouldn't, like that hydrogen in the ortho position. If it deprotonates, think of an E2 reaction. So let me put this in quotes. That pair of electrons would go there, the chlorine would be kicked off. So if the hydroxide deprotonates that ortho hydrogen, I'm going to make what's called the benzene. And this is how this reaction, all the evidence is this is how this reaction goes. The benzene has big issues because having a triple bond that's supposed to be 180 degrees in a cyclohexane ring is going to be really unstable. But then again, this is at 350 degrees, so it's probably going to be unstable. So what's going to happen then is my second equivalent of hydroxide. So when I do this reaction with hydroxide, the hydroxide is going to be in excess. I'm going to have a ton of it. The hydroxide can either come in and add to the paracarbon, or the hydroxide can come in and add to the orthocarbon, or sorry, the metacarbon. So now I'm going to call this the paracarbon because of the methyl group. I'm going to call this the metacarbon because of the methyl group. So it could add to either one, and there's no preference for adding to one or the other. So if that happens, then if I write out my benzene, the OH minus, if it adds to the paracarbon, this pair of electrons goes back to the metacarbon, so that I end up adding the OH group. I now have my double bond, but now I have a negative charge on that carbon. If I come down here and I add the OH minus to the metacarbon, I'm going to do exactly the opposite. So I basically am going to get both of these anions when the hydroxide adds to the paracarbon or when it adds to the metacarbon. And then the final step in this is going to be for the water, for the C minus to deprotonate the water, which we normally try and avoid, but in this case, it's going to be the final step. So if I write this as an HOH, that C minus is going to deprotonate the hydrogen, and I'll have added the OH para. And again, if I have water here, the minus charge will deprotonate the hydrogen from water, so that I'll end up adding the hydroxide group meta to the methyl group. So the evidence that it's a benzene intermediate is because you get both of these products. You get both of these products 50-50. So you get 50% and 50%. That's evidence that you end up with a benzene intermediate. So what I'm sure that the first person that did this reaction didn't put a group here, and they just got one product. And then when they're thinking about the mechanism, they said, well, we need to put a group here to make sure we just get one product. And then lo and behold, they got two products. So then they were like, okay, I need to readjust my mechanism to figure out what the mechanism is to account for the fact that we get 50-50. So this mechanism would be what you would write for any kind of deactivated ring.
That makes sense. Thank you.
What else? I just remembered what I did not put in the folder for today's lecture is I didn't put a explicit to-do list, which I will do right after this. because I posted the video, and did I post the lecture notes? I think I did as well. That's a bad move, because then people can just print out the lecture notes without watching the video. But is there a tremendous lag time when I draw and when you see it? I think it depends on your internet. And it's 8 in the morning, everybody's still sleeping and nobody's gaming and watching Netflix and whatever it is that they're doing to amuse themselves. Homeschooling. Anything else? Okay. So the quiz on this material is due by midnight today, and then the video is already posted. I'll put the explicit to-do list on for the stuff for Monday that replaces Mondays, and I'll probably get caught up over the weekend with some videos, so I won't be putting them on at 8 o'clock the night before. So that's why I'm staggering everything else, because I know at this point it's kind of hard for me to keep up. So, all right. Anything else? Okay, let's see. So any questions, email me, put them on Piazza. I did record this, so I will figure out how to upload this. And then people can look at, because now they're going to be like, we have to watch 2 hours of videos. I don't know. But they can look at the notes, and if there's something there, they can fast forward, because I'll try and get it on YouTube. And then who knows how many other college students are watching my superior videos to everybody else's. At least when we have an online class, we'll know the reason. Then we know the reason why to take it here as opposed to someplace else. And I'm joking about that, maybe. Okay. All right. If you have any questions, because let's see, we're over our allotted time, and Dr. Martin would say, don't stress people out unless you had a question. Okay. All right. If you have any questions, and you can use the You Can Book Me to make an appointment, and we'll do one-on-one or small groups with this. If there's anything you would like to go over, like NMR problems or something like that, and you have stuff written out, you may want to take a picture of it and send it to me, so that way I can pull it up on the screen when we talk about it. Okay. All right. 1 week in the can. Just a lot more to go. So, all right. I will see you whenever I next see you.
Sounds good. Thank you.
Okay.
Thank you.
Bye.